So the focus of this video and your practice problems is going to be divisibility rules. It's good to be familiar with as many divisibility rules as you can. They are helpful ways to quickly check if a large number is divisible by another smaller number when you don't have the time or want to take the time to divide it out completely to see if there's a remainder. These are the rules 2 through 11. Those are the ones that I suggest you become most familiar with. We're going to look at some problems in the video, and then you're going to do some follow-up problems that apply these rules. But in addition to that, we're also going to play with some other number theory and divisibility concepts that are related to this. Knowing how to apply these rules and think about a number's factors or characteristics just in general will help you in a lot of ways to solve problems more quickly, to represent numbers in ways that might make the solution easier to see or more elegant, to recognize patterns, things like that. If you're not familiar with these rules that are on the screen, you might want to take a second to pause the video and copy them down, or they're also on the extension portion of the practice plans. So if you have a copy of that, you can reference them there. You might have seen some of these before, but you will definitely need to reference these as you go through your problems. So with that, let's go on to the problems for the video. So our first problem says, using each of the 4 digits 2, 4, 6, and 8 exactly once, how many 4-digit multiples of 4 can be formed? So the divisibility rule for 4 tells us that we only need to look at the number formed by the last 2 digits. It doesn't matter how many digits precede those last 2, as long as they're divisible by 4, the entire number will be divisible by 4. So to start with this problem, let's just look at how we can rearrange those numbers to create 2-digit numbers that are multiples of 4. And if we go through that strategically, we can start with 2 in the tens place, and we know we can form 24, and then 4 more than that, we can form 28, and that's all we can do with 2. Then we can move on to 4, and we know 48 will be divisible by 4, and then 4 less than that would be 44, but we can't use 4 twice, so we're good with 4s. Then we move on to 64, we have 68, and then last we have 84, and again 4 more than 84 is 88, but we can't use that digit twice. So those are all of the 2-digit multiples of 4 we can form using those 4 digits exactly once each. So using those 2-digit numbers, now we need to figure out how many 4-digit numbers can be formed. So for every 2-digit number, we are going to have 2 remaining digits, and there's 2 ways we can create a number using those. For example, 24, we have 6 and 8 left over, so we can make 6,824, or we can make 8,624. So knowing that each of those 6 2-digit numbers can then be created into 2 different 4-digit numbers, we can conclude that we're going to have 6 times 2 equals 12 4-digit multiples of 4. And if you don't believe me, there are the 12 4-digit multiples of 4. You can go through and check them. Our next problem reads, how many zeros are there after the last non-zero digit of 125 factorial? So what 125 factorial means, if you're not familiar with factorials, that little exclamation point is not a typo. It basically just means you start with 125 and then you multiply every integer 1 less than that until you get down to 1. So 125 times 124 times 123 and so on until we multiply through by 1. And our question's asking how many zeros are there after the last non-digit 0 of this product. In other words, what we're really looking for is how many factors of 10 are there in this product, because a number with 1 0 we know at the end is going to be divisible by 10. If it had 2 zeros at the end, you would know it's divisible by 100, or 10 times 10. If it had 3 zeros, you'd know it was divisible by 1,000, 10 times 10 times 10, and so on. And the prime factorization of 10 is 2 times 5. So we can break this down and look at how many occurrences of 2 and 5 we have in this entire product. So since it's all of the numbers 1 through 125 multiplied, we know that every other number is going to be even, which means it's divisible by 2. So we're going to have at least 62 2's in there, because 124 divided by 2 is 62. So we're going to have at least, we can factor out at least 62 2's. So now let's look at the 5's. So if we just look at every fifth number, so we have 125, 120, 115, 110, etc., all the way down to 5. We'll see that our first number, 125, is 5 times 25, 120 is 5 times 24, 115 will be 5 times 23, and so on until we get to 5, which is 5 times 1. So there's 25 multiples of 5 there. But there are some additional 5's we aren't counting. So let's look at multiples of 25, which will have that additional 5 because it's 5 times 5. So 125, 100, 75, and 50. 50 and 25 all have another 5. We've already counted 1 5 for each of those, so let's divide them by 5. So if we divide all those by 5, we end up with 25, 20, 15, 10. And then writing those out, we have 5 times 5, 5 times 4, 5 times 3, 5 times 2, 5 times 1. And if you count up the 5's, each one has an additional 5, and then 125, we had another 5. So there's 6 total 5's that we missed in our first counting. And that is all of our 5's. We know that since 125 is 5 to the 3rd power, any number that would have 3 5's as a factor would be equal to or greater than 125. So we know we have counted all of our 5's, and our final answer is 25 plus 6 equals 31 zeros. And as we said earlier, we know there's at least 62 2's. So for each of these 5's, we have a 2 to pair with it to create that factor of 10, which will give us a 0. So at the end of this, we're going to have 31 zeros. All right, so for our last problem we're looking at, it asks, what is the greatest number that evenly divides the sum of any 6 consecutive whole numbers? So let's call the first number of this arbitrary set n, the variable n. Then we know that our next number is going to be n plus 1, the number after that's n plus 2, then n plus 3, n plus 4, and n plus 5, since they are consecutive integers. So if we then sum them up as the problem asks for, combine our like terms, we get 6n plus 15, which we notice is divisible by 3. So we have now proved that any any set of 6 consecutive whole numbers is divisible by 3. Do we know that this is the greatest number, though? We can quickly prove that just by coming up with a test case. So if you actually just think about, let's look at this set of 6 consecutive whole numbers, -1, -2, 0, 1, 2, 3. If you sum that all up, it equals 3. So it is divisible by 3, but is not divisible by anything greater than 3. So that alone tells us that 3 is in fact the greatest number that evenly divides the sum of any 6 consecutive whole numbers.